Assalamualaikum and hi. Today we will look into the lecture number 12, static correction. Okay, for the previous week we already looked into the lecture number 11, which is the stacking. Yeah. So in this lecture, basically we will look into how to correct for the land acquisition dataset. Okay. At the end of this lecture, basically you should be able to differentiate between general static as well as the residual static, discriminate the suitability of the datum correction, as well as perform the static correction method on the real seismic dataset, which is contribute to the following course learning outcome, as well as mapping to the following program outcome. So where does the static correction coming in? It's basically coming here after the multiple attenuation process. Yeah. As I mentioned earlier, static correction mainly been used in the land acquisition. However, in the marine acquisition, we occasionally apply the static correction in order to prevent some near surface problems. So actually the seismic reflection data in different traces are not always lying on the hyperbola or horizontal reflector. As mentioned by this, as you can see from this image, this image especially on the land dataset, the source and the receiver is not on the same level. Unlike in marine dataset, marine acquisition, the source and receiver will be within a same layer. In other words, generally they will be 6 meter or 5 meter beneath the water layer. In the land acquisition, your source and receiver, okay, your source as well as the receiver is not on the same level. Okay. Consequently, your output, your short gathers will be on a different level. Okay. The reflected data have a certain displacement with a different length of the ray path, which is called the static displacement in the data. Okay. So the topography, which is the different level of the earth undulation, will give a differences in terms of the elevation. The existence of the weathered layer or unconsolidated layer in the green color, okay, in the orange color, has a relatively slow velocity compared to the subsurface. On the other hand, if you use in the boreholes, okay, if you use a borehole in the land acquisition, or having a different gun and cable depth in marine, this will also cause a statics problem. Okay. One other thing, in the marine acquisition, you have the tidal wave, which we generally corrected in the earlier part during the seismic data processing. Alright. To correct for the near surface condition, the affected subsurface travel time and amplitudes, therefore we need the statics correction. For more accurate structural interpretation of the seismic data, otherwise you will get a lot of jittering in your seismic data set. The anomalies, okay, in this case, generally if you have a shallow gas problem, we also sometimes apply a statics correction. Data quality, particularly the CMP stack interpretability, depends on the proper static correction. And therefore, the static correction needs to be iterated with the velocity analysis. I will show you later the process that we conducted during the seismic data processing in order to improve the statics problem. So, what is the main objective of having the static correction? It's basically to adjust the seismic traces in such a way that the sources and receiver are present at one horizontal level. Okay. Therefore, the travel times of the separated traces need to be corrected, which is came into two different types of the static correction. The first one is the general static, okay, given over here, which is the whole trace. In other words, a single short gathers, for example, this whole single short gathers will be corrected with the same time shift. Okay, means that all these traces will be corrected with using a single value. In the dynamic correction, another type of the static correction, we will using a different time window of the traces. Okay, in other words, each second or each depth of the traces will be corrected with using a different amount of the static correction. Okay? This will result in stretching and compression of the events, okay, such as the enamel correction. We will look further in the next slides. The difference between this general static correction and the residual static correction is given by this table. In general static correction is generally applied in the early stage of the processing, while the residual static generally applied in the later stage of the processing. In the earlier stage means that generally we apply the static correction just before the noise attenuation or just after the noise attenuation. Meanwhile, the residual static generally was conducted after we has finished the multiple attenuation process. The general static correction generally applied to topography and influence from the weighted layer. Okay, in order to remove the weighted layer problems, while the residual static implement after the general static were applied, which is at the later stage of the processing. The general static solve problem for only a certain part, while the residual static generally solve the whole statistics problem. Okay, general static need small shift correction, while the residual static compute surface consistent static shift one trace delay. And general static has the advantage of correcting long period statics, while the residual static generally will correct for the short period statics. This is an example of the static correction. Before static correction, we will see our reflection, okay, in this case, has been going up, going down, going up, and again. Okay. This is due to this weighted layer, okay, this weighted layer, which caused these particular problems. However, once we have the static correction, all the problems, all the irregularities within the trace now will be covered, will be corrected to a single datum level. Okay, the datum level is basically the one that we need to specify during our static correction. Right. Before static correction, reflection are not lying on a hyperbola, and after the static correction, the reflection appears as if the source and receiver has been positioned at the datum level. This is the datum level. Right. Okay. What is datum plane? Then or datum level? Okay, it's a desired result of the static correction by correcting to the flat datum. Okay, the flat datum, which is given by a level or a layer that is defined by a geophysicist. Means that a processing geophysicist need to define which is your datum plane. Generally, we choose a datum plane underneath the weighted layer. Okay? In other words, you eliminate all the weighted layer. After you do the static correction based on this datum plane, your traces now align at a nice hyperbola. Okay. Alright. So the template is basically a fixed reference level at a time is equal to 0, which is an arbitrary planar surface, usually flat or smoothly varying, serve as an agreed and known references, upon which source and receiver are assumed to lie after the processing takes place. Therefore, we have the three types of datum plane, which is the horizontal seismic datum. You choose a horizontal one, or it can be a tilted lenses survey seismic datum, or it can be a floating seismic datum. It's given by here. Okay. Although it looks more difficult, however, this floating seismic datum is actually the most accurate datum plane, as we have the velocity accuracy will be increases, okay, compared to the fixed datum plane. How do we calculate this static? Okay, actually we need two informations from the seismic data. The first one is the thickness, and the second one is the velocity. Okay. How do we determine these two information? Okay, first of all, we need to determine the layering velocity. How do we determine that one? By using a information of the direct arrival as well as the refraction. This will give you the information of the weathering layer. Okay. Another method is by using the topography, by using the elevation static or uphold correction as well as the refraction static. First one, using the elevation static, it's actually a vertical aligning of the different elevation of the sources and the receiver, which is given by the short static equal to elevation of source minus the elevation of the reference level divided by the velocity of the subsurface, or the receiver static, which is the elevation of the receiver minus the elevation of the reference level divided by the velocity value. Therefore, the total time correction is given by the short static plus the receiver static. This will give you the total value of the correction required. Next method is by using the uphold correction. If you're having a borehole, then it's very useful to use the borehole to identify the static value. When a shot is fired, okay, in this case the shot is given inside this borehole. The travel time to the surface is recorded and consequently velocity of the weathered layer can be estimated. Okay. Therefore, from this point, in this case, you have different depth value which is recorded by this receiver, and therefore you will get a different point on your graph, which is after you can do a single line and calculate the velocity from the line. From here, you can easily identify the weathering velocity, the thickness, as well as the velocity below the weathered layer. Next one is by using the refraction statics, which is the correction for the weathered layer. By using the first break of the certain shot, a model can be constructed for the weathered layer in terms of the velocity and depth. When the distance between the receiver is too large, sometimes the supplementary refraction measurement are carried out. Methods to determine the velocity and depth of the weathered layer either by using the delay time, using the generalized reciprocal method, or using diminishing residual matrices, which is these three methods we already learned during the seismic method course. Some important information that you need to still remember is in terms of the critical angle, which will give you the head wave or the refraction wave. Okay, it's given by this formula: sin alpha over sin 90 degree equal to v1 over v2, which is equivalent to Snell's law. Hopefully you still remember this one. So to correct for the static correction method, if you use this particular information, the slope of direct arrival is given by 1 over v0. The slope of the refraction arrival is given by the 1 over v1, and the intercept time is given by t1 equal to h0 2 cos I divided by velocity, okay, which give you the information of the intercept time. Next, we look in terms of the first arrival and refraction. Okay. The direct arrival is basically the signal from the source straight to the geophone. The refraction is basically, as you know, the head wave that travel throughout the subsurface, between the layers, and you can determine the velocity based on the slope, the gradient of the graph that you produce. Direct arrival, first refraction, and second refraction, you can easily identify the velocity of the particular layer. So how do we determine the velocity if we are using the software? First of all, we pick the refraction signal and we plot that particular peaks and find the straight lines to determine the velocities as well as the thickness. Okay, this is one example of the first break peaks. Okay. So you can see all the red dotted over here is basically the first break peak. From here, basically we can identify the near surface model. Yeah. This method is particularly useful if you in diving with tomography techniques, which is one of the method to solve for the near surface anomalies such as the shallow gas cloud. Okay? By using this diving with tomography. Another example of static correction. If you can notice before the refraction static and after the refraction static, okay, you can see the difference before and after. After the refraction static, now you no longer seen this particular difference level. Okay, now after you apply the refraction static, all throughout the layer having a equal or a similar depth. The residual setting is basically shifting the separated traces to obtain the optimal reflection. It is to ensure traces of single common midpoint are not shifted randomly. Therefore, the shift is divided in a value for the source and a value for the receiver. For each source and the receiver, a value is determined, which is, in other words, is not applicable to all. Okay, we identify each particular source and each particular receiver to do the residual setting. All traces with a certain source are corrected with the value for that source. Similarly, all traces with certain receiver are corrected with the value for that receiver. The resulting shift or the resulting static correction of a trace consists of the correction value of the source and receiver of the corresponding trace. Okay, we do it individually. When we implement this particular residual static correction, it's not only a straightforward process. Okay, we do it iteratively in order to get the best output from this residual static correction. Okay, if you can see from this workflow, once you have the CDP gathers with the statics problems, you do the velocity analysis, apply the animal correction, and you compute the residual statics. And once you apply residual statics, we do the second velocity analysis, animal correction, and we compute again. Next, we apply the residual static to the original data set, and we do the same process all over again until we find the minimum residual statics value. This is an example of the residual static correction. Okay. In the step 1, you build the model trace by summing all traces from several move out corrected CDPs. Second one, you measure the trace shift by cross correlation with the model. Okay. By cross correlation, the keyword here is cross correlation. You cross correlate the traces of the model traces with the other traces. Okay, and finally we compute the surface consistent statics from trace shift and apply to the traces in order to align the events. It's a real seismic data before and after residual static. If you can notice from this part, okay, it's very jittery. Okay, you have a lot of statics problem. You can notice clearly, and after you apply the static correction, the events become aligned in a nice horizon. Another example, after you apply a general statics and with the residual statics. Okay. Another quick way for you to identify the statics, you can easily see from this particular image. If you notice this problem, okay, this particular issue, as well as this particular issue, and then it will give you the information of the static problems. Okay, just the misalignment, okay, the abrupt changes, it is actually giving you the statics problem. Another example, you have the structure of shallowest reflector repeated in the deeper events. Poor reflection quality may due to the improper static correction, not necessarily due to the issues such as low amplitude and so on, but it might due to the statics problem. Bad static correction means that the bad velocities and bad stacking. Okay, therefore you need to do you need to apply a static correction in order to have a good velocity output. Changes in the near surface topography can also cause the static problem. As a summary, statics are near surface conditions that affect the travel times and amplitude of the subsurface reflector. Therefore, it is actually a key to the better seismic interpretation. Without proper static correction, seismic data may have poor reflection quality. The subsurface anomalies can caused by the near surface effects. Static correction may hamper the velocity analysis and slow the data processing. And there are two types of the static correction, either using the general static correction or residual static correction. That's all for today. I hope you can learn as much as possible. If you have any question related to static correction, please don't hesitate to email me, as I will be away for the whole next week. Thank you very much.